Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this chapter, we're going to be talking about simple linear regression, which is the measurement of the impact independent variables have on a dependent variable. It's going to be one of the first forms of predictive modeling that we encounter in this class. In a cause and effect relationship, the independent variable is the cause and the dependent variable is the effect. And the method we're going to be looking at today is the least squares linear regression. It's a method of predicting the value of the dependent variable based on the value of the independent variable. Now in this chapter we're going to be focusing on just one simple independent variable, and that's why it's called simple linear regression. In the next chapter, we're going to have multiple independent variables, and that is multiple variable regression, and we'll be covering that as well. Now, in our last chapter, correlation did not distinguish between different types of variables, but in regression we do. There is always a designated predictor variable, and then one or more explanatory variables. The purpose of regression is to make predictions. That's why we do linear regression in the first place. And as I've said, this chapter, simple linear regression, involves a single predictor variable. Multiple regression involves models that have a single predictor variable but two or more explanatory variables. That's what we're going to be covering in the next chapter. Simple linear regression is appropriate when there are three conditions that are met. The first condition is that the dependent variable has a linear relationship to the independent variable. You'll be able to tell this by looking at a scatter plot diagram and seeing the relationship between the two. I'm going to explore that when we do an example in 9. And we'll cover the residual patterns in a future chapter as well. And then for each value of x, the probability distribution of y has the same standard deviation. Again, this is going to be satisfied relatively easily when we look at a residual plot diagram and see the distribution of the values. So we'll see both of those. And finally, the third condition, for any given value of x, the y values are independent. And again, we're going to see the residual plot when we do our regression to see that that is in fact the case, and that the y values themselves are roughly in a normal distribution. The dependent and independent variables need to be measured on an interval or a ratio scale. Categorical predictive variables with two categories like on-off can also be used because they can be basically treated as numerics, on-off, 1, 0, yes, no type of variable. Let's start by explaining the process mathematically. Linear regression finds a straight line called the least squares regression line, LSRL, that represents the observations in a bivariate data set. So suppose y is a dependent variable and x is the independent variable. The regression formula, and this is the formula you're always going to see, b of 0 plus b of 1 times x1 plus e1, where b0 is going to be a constant number, b1 is the regression coefficient, x is the value of the independent variable, and e1 is the residual left over after the computation of y. Okay, yes, that sounds and looks really complicated when you try and put it into words. But when you see it in practice, it is actually quite simple. And when you see how we do it in KNIME, it's even easier. So let's try and demystify this process. Now, just some statistical jargon you heard me refer to bivariate data. When we're looking at only one variable, we say that we are working with univariate data. And when we are looking at two variables, we say we are looking at bivariate data. So let's look at that formula again, this time when you see a graph superimposed upon it as well. We see that the y-intercept is at 20. That's the value of b0. That's where the regression line intercepts the y-axis. The E1 value is the residual based on the computation that we have done. And the b1 is the slope of the line multiplied by the x value, by the independent variable. And so multiplying the independent variable times the slope, adding the residual value back, and taking into account the intercept. This is basically all that's necessary to do a regression model. So using the formula that we've now got, let's plot a prediction. So we can see that y is equal to 20. And b0 is equal to 20, and b1 is equal to 2. So if x is equal to 15, then y is equal to 20 plus 2 times 15, the slope of the line. So y would be equal to 50 in our prediction. And when you look at the intersection of those lines where x is equal to 15, y is equal to 50, you can see the dotted line there connects those 2 points, and that's our prediction based on the formula that we've created. So a bit of, again, statistical jargon here. The regression parameters b0 and b1 are defined and explained. What we are doing with that regression line is we're minimizing the sum of the squared differences between the observed values, y, and the predicted values. And that's what the regression line is supposed to represent. The regression constant is always going to be the y-intercept. The regression coefficient is always going to be the average change in the independent variable. In other words, the slope of the line. Of course, computers have changed the landscape of everything we do, and using tools like Excel and SAS, etc., 9, you don't need to understand the regression formula. You only need to understand how to interpret its output. That's what's so great about the modern analytic world that's happening today, is that there is a lack of necessity in understanding the formulas and instead being able to interpret the answer. So there are 3 conditions that are required in order for you to use simple linear regression. There has to be 1 independent variable and 1 dependent variable. The variables must be on an interval or ratio scale, and the correlation between the variables must be linear, in other words, not curvilinear. Remember the example of age and strength. So those 3 all conditions must exist in order for you to be able to use simple linear regression. Let's use an example here. Could we use simple linear regression to predict IQ from test scores? Well, the number of variables is 2, so that condition is met. The measurement scale is of an interval or ratio, and the relationship is linear. So yes, I can make this, and I can use linear regression in this example. The coefficient of determination, denoted by R squared, is the key output of regression. R squared is interpreted as the proportion of the variance in the dependent variable that is predicted from the independent variable. The interpretation of R squared is actually fairly simple. It's going to have a value between 0 and 1. And R squared of 0 means that the dependent variable cannot be predicted from the independent variable at all. And R squared of 1 means the dependent variable can be predicted without error from the independent variable. And anywhere in between 0 and 1 indicates the strength to which that prediction can be made. For an example, R squared of 0.10 means that 10% of the variance in Y is predicted from X. The other 90% would have been predicted by some other independent variables. The coefficient determination, the R squared value, is related to correlation. It is basically the correlation coefficient squared. So if we had the correlation coefficient equal to 0.5, then that value squared would become 0.25. So the R squared value is just the R value brought back from correlation. That completes this chapter of the class. Feel free to move on to the next chapter.